Um, okay, so welcome to the IAMP Mathematical Physics Seminar. For the people who joined us for the first time, the seminar it takes place online every 2 weeks and is organized by the International Association of Mathematical Physics. And if you didn't do this already, you are very welcome to visit our webpage to see all the other activities. Today's speaker is Annalisa Panati from the University of Toulon, and she will talk about entropic fluctuations in quantum two-time measurement framework. Thank you very much.
Thank you very much, Margherita, for
You're
the
there.
introduction. So first, thank you very much for this invitation. I'm honored to be here today, and I'm happy to present a series of recent results obtained in collaboration with Tristan Benoit, Laurent Bruno, Volkan Jakšić, and Claude Lampilet. So these results are written in a series of 4 papers. You find the references here. 2 are already published and 2 are still under review, but are available online. And my goal today is to put this result in context and to walk you through the main ideas. So the context of we're working in is the extension from the classical to the quantum setting of some groundbreaking progresses that happened in the 90s in non-equilibrium classical statistical mechanics. And we will see in the attempt to obtain the quantum version, it has been understood that one needs to introduce the so-called quantum two-time measurement framework, which is a very natural framework. You basically have to measure twice, but it comes with the price of some surprising and unexpected phenomena, which have no classical counterparts, and some of them will appear in the results of today. So I organize the material as follows. I want to give you a quick description of these progresses that have been done in the 90s. They go under the name of the fluctuation relation. I will not attempt to cover all the aspects. I will only give a quick review in order to cover the aspect I need in order to explain our results. There are 2 versions. There is the transient version and the steady version. We will see what that means. In the attempt of quantizing the transient version, it was understood that one has to introduce the two-time measurement statistics. We'll see what that means too. Our results concerned the steady function. So thanks to some mathematical formula that we are able to make a proposal for a quantum steady functional, which was missing from the literature. And so once it's done, then we have a result on the behavior in this case. So we will see it will be natural to ask yourself the question of what happens if instead of taking direct measurements, you would consider a setting where, sorry, I'm still practicing with this pen, indirect measurement. And so we'll see that's a very natural question. And in the last part of the talk, I will tell the result we have in that second. So let me start with this fluctuation relations. So we are in the context of classical non-equilibrium statistical mechanics. So classical system is described by a phase space and a dynamic on the phase space. And because we are dealing with system with many particles, we don't have the details. The state of a system is described by a probability measure on the phase space. So we are in the non-equilibrium setting. So you have to think of an explosion, or you have to think of a river flowing. So the another typical example we have in mind, which is also the setting in which we are our results, is the so-called multi-thermal system, or also called open systems, where so you have to think of a situation where we have two reservoirs which are initially at equilibrium at a different temperature, beta 1 and beta 2. Okay, and then at some point you can connect them either directly or through a small system, and then we will have an evolution through the perturbed dynamics. Okay, in the situation we have in mind, we don't expect this system to ever reach equilibrium. You would expect that after some time it may reach a steady regime in which you will have a flow of heat particle entropy from one reservoir to another. Okay, so in this context of non-equilibrium, it is convenient not to think in terms of entropy, which may be ill-defined, but to think in terms of relative entropy, which is described, which is a function of the Radon-Nikodym derivative, of the two states. Okay, so it basically tells you what weight of the state nu gives to a certain portion of the phase space with respect to what it was given by the previous state nu. Okay, so now the second law of thermodynamics tells you that entropy always increases. I mean, the choice of the sign choice, the sign convention I used that will translate in the fact that then the entropy production is always positive. Okay, but this is one has to understand that the second law of thermodynamics is a statement in average. So on average, the entropy always increases. Here we are in a non-equilibrium situation. Therefore, it could happen that our system for a short time maybe will go through a configuration where the entropy actually increases. So in this context, we want to be more precise, and one needs to introduce to identify a random variable for which this the mean entropy, so this quantity is the mean with respect to the certain probability measure. So okay, so this would be the variable, okay, that can be viewed as entropy production. So we are seeing the phase space as a probability space with respect to the measure mu, and then a function over this phase space is viewed as a random variable to which you can associate a law which will tell you the probability of having an entropy increase or an entropy decrease. Okay, and on average, the average will be always positive. So now what can we say about this measure? Can we make some precise statement? And progress started in the 90s, with some numerical experiments, and then in 93, and then in the year following year, there were two sets of theoretical explanation, one in the group of Evans-Sayers and one proposed by Galavotti in two different frameworks. There is also a related literature in work, where instead of entropy you look at work. You may have heard of Crookes or Jarezinski. And there is also the forgotten work of Vukov and Kuzolev that I mentioned to you it was forgotten but rediscovered. I mentioned to you for a very specific reason that we will see later. So this seminal paper opened a vast area of research. There has been a lot of work on this subject. I am just telling some aspect from a very specific angle, which is the one that I need in order to explain you our result. And I will also follow in the point of view which has been advocated and I've learned in the paper of Jaksic, Pillet, and Rebele in 2011. So, but I would say there is agreement in the community. We can see the following, the so-called fluctuation relation as a statistical refinement of a second law of thermodynamics, so statements which go beyond the average. And it is what the fluctuation relation says, that the probability of having entropy decrease is not zero but compared to the probability of an entropy increase, it will be exponentially small with respect to the size of a perturbation. So it's not zero, but it becomes small if you want an increase. So this is supposed to be considered to be a universal property for a time reversal invariant system, and can be proven very general. For example, in our setting where we take as initial state an equilibrium state or a multi-terminal state, then this is true. So I want to emphasize this is an exact relation. It's not more or less exponential. This is an exact formula, and therefore it can be. So this version is the so-called transient version, and because it is an exact relation, it can be also written as the symmetry of a certain associated functional, which is the Laplace transform of the measure. So now it's always nice to have, this is viewed as a fundamental law of physics. It's always nice to have a fundamental law of physics associated to some symmetry. People like that. But there's a reason why it's convenient to write it through this functional is because this is a well-known object in probability theory. This called moment generating function and the associated functional. Can be used in large deviation theory. The limit of this function, the limited object, gives you, typically via Gardner-Lassley's theorem, the large time behavior of the fluctuation of the mean entropy change. Okay, so some of you know this. Typically, we'll have a large deviation principle with a rate function, which can be computed using this limiting object. So, for those of you who are not familiar with large deviation theory, then let's say that just this object encodes the large time behavior and fluctuation of this random. Very good. So now we turn to let's turn to the steady version. So the steady. So this is the steady version where was written in a different conceptual framework. When one thinks that what is relevant in this non-equilibrium situation is not the initial state, but the steady state. So the property of a non-equilibrium system is captured when once you have reached the non-equilibrium steady state. So steady the regime I was telling you before. Okay, so before we have the initial system, now we let evolve the system for a very large time, and the idealization of that is that we take the limit for t going to infinity. Because once you are in this non-equilibrium steady state, then you look at the fluctuation. So then one can rewrite the same functionals, but this time we do it with respect to the non-equilibrium steady states. And then we also have a limiting object. So in this case, the symmetry is not true at finite time in general, but the equality is restored, the symmetry is restored when we take the object. So what is expected is that if you have a strong chaoticity, if your system is chaotic enough, then you would expect that these two functional are the same, and therefore this one inherit the symmetry in which is satisfied with this one. Okay, so this has been proven in some paradigmatic models, and it is expected to hold true on the stronger DCP hypothesis to the point in some authors, in the review that I was mentioning before by Jacques Pilet and Rebellet, it is advocated I can take this property itself as a chaoticity property that should be expected in natural system. They call it the principle of regular entropic fluctuations. Very good. So now we want to quantize all this. So what the the problem of quantizing this result has turned out to be more difficult than expected. So before there were several attempts. So one first didn't work, we called the naive quantization, and then you will see why, and then we'll go to a different attempt. So let me first throw some notation. So we have we assume in this talk we have only two reservoirs, which may be coupled directly or through a small system. The small system is finite. So we will switch between two ways of describing the reservoirs. So the reservoirs are infinitely extended in our setting. So in principle, we should describe it in an abstract way through the algebra of operator, the dynamics, and the equilibrium state is expressed by a K-mass condition, but it is also possible to use some finite, the so-called confined approximation. So you can approximate your reservoir by a system which is the Hilbert quantum system. The Hilbert space is a space of a finite dimension. And here, then you can write explicitly the initial state will be just the Gibbs state at a certain given temperature. And the small system, of course, is small, so the two descriptions are the same as a finite dimension. So we are thinking again of our initial state is the product state, and we're having we will have a free dynamics because we think that initially you are at equilibrium, and after one connects the two reservoirs, then we would have a perturbed dynamics. And if you have a Hamiltonian description, it's just H0 plus V. Otherwise, you can write it in abstract term through this generator. Okay, so what is the naive quantization? So naive quantization is the first thing you would do. So you would simply replace, go through the customary way of doing quantization, replace one operator with the corresponding object. In order to motivate, is really something very natural that you would do. It is what Bukov and Kuzolev did in the 70s. And then their work somehow was forgotten, or maybe because at the time so they were in Russia during Cold War, or because the time were not ready to understand maybe that work. Anyway, this work was forgotten, and so the same attempt happened again in the 90s. We call it now we call it in our group the naive quantization. So and then the work of Kuzolev was again rediscovered. So let me try to give you the main idea in a simplified setting where I can identify the entropy. So we can write this would make sense. So if you are in a finite setting, and if your initial state is it's basically the Gibbs state, then I can identify the entropy essentially with this operator. So the corresponding object in this naive, the object you want to look at in this naive approach is, this one is the operator, which is the difference of entropy and entropy evoluted at a certain time t. And you consider the spectral measure associated to this operator. Okay, that's what we would do. Right, so then you can define the topic functional as you did before with respect to this measure, and this is perfectly fine. What happens is that if you follow this line of reasoning, then you will not, sorry, this is not working. Okay, this leads to a theory that does not satisfy the fluctuation relations. And this was viewed as a huge fail because by the time the fluctuation relation were considered statistical refinement of second law of thermodynamics, a very fundamental law. So I want to remark again, so we, in this naive approach, one try to associate to the entropy an observable the fact that this approach fails in the work-related literature is often expressed by saying that the work cannot be defined as an observable. So we have to find an alternative approach. So what breaks so then there is we have to try a different point of view. There were two separate lines of thinking, one purely from a mathematical point of view and one from a physical point of view, which ended up to give the same result. So let me start first with the mathematical point of view. So this was the work of not Hal Tasaki, the other Tasaki, not Hal Tasaki, sorry, I can't pronounce the name properly.
Shinichi Tasaki, yeah.
Thank you very
Not
much.
Me, not my
Yes.
relative.
Thank you very much. So this is the work of Tasaki Matsuita of 2003. And the main idea is that when you go back to what the entropy production was. So the entropy production, as I tried to emphasize before, is expressed in terms of Radon-Nikodym derivative. And so the idea is now that you should not split this, like before we have log omega t or log omega, but we should really look at what is the quantum Radon-Nikodym derivative in the abstract case. And so this go back to, it's an idea that goes back to the work of Araki in the 70s, that what corresponds to the Radon-Nikodym derivative here is the relative modular operator, that therefore will appear in the quantization. So now I think the audience is split in two parts. Those of you that know what the relative modular operator is, and those of you who don't know what the relative modular operator is. So in my view, the best way to give an intuition what it is exactly that, is to say that is the object you need in order to have an equivalent of a Radon-Nikodym derivative. So here, the Radon-Nikodym derivative would let you express the, I'm sorry, I cannot write well with this. So here, this object was the one would allow you to express, you can express expectation value integrable of a classical observable. When thanks to the Radon-Nikodym derivative, you can say this is, you can express this as the, you can go from expectation values of omega t to expectation value of omega thanks to the Radon-Nikodym derivative. And this object will have the same property, but now you don't take expectation value of function, you take expectation value state evaluated over an observable. Okay. So the problem, slight problem of this relative modular operator is that you cannot really write it it does not belong to the algebra. So in order to write it, you need to use a representation of the algebra. If you want to have something which belongs directly to the algebra, you need to use this cousin, which is a slight modification of a relative modular operator, which we call the cocycle, the entropy cocycle. So now this approach, which is, as you see, is a purely mathematical point of view, leads you to a theory which satisfies the fluctuation relations, and then you can take, you can see this object as the Laplace transform of a probability measure, which will be the spectral measure of this operator. And this is perfectly fine, perfectly nice, except that it is not clear what would be the physical meaning of the measure P omega t that appears here. So that's why there was a parallel line of thinking, which is start from a physical observation. And it was first pointed out by Kurchan in 2000, and that the idea was developed also by Hal Tasaki. And this is the observation, which the key observation is that in what we have done before, what I have presented to you in the naive approach, we have never measured the system. So the measurement on the system has been neglected, okay? And that's not what you should do. What you should do is to consider not the spectral measure I showed you before, but a completely different object, which is called the two-time measurement statistics, which is defined as the difference, the probability distribution that you take to obtain if you consider the difference between two measurements. Let's go through what that means. So this is a very natural object to take, and as a matter of fact, it was considered already in other works which are not related to the fluctuation relation. For example, in the work of, you may have heard of the work of Lezovic and Levitov, there they call it the full county statistics, but it is the same thing. Okay. So let me describe what this means. We have to work in a confined system in order to everything to make sense at first. If I have an observable, the protocol that you need to use to construct this measure is simply you take an observable. Okay, so here I am in a finite dimensional, so I just have diagonalize the observable, so we will have the expectation values. The protocol is the following: you measure once, you will have a certain outcome at, you measure once at time 0, you will have a certain outcome, and you let the system evolve for a time t, and you perform a second measurement, which will have some other outcome, ak. And then the probability, the two-time measurement distribution of A is just the probability of measuring a change in A equal to phi if I follow this procedure. So you see, it's not very difficult, you know, it's a quite natural setting. This approach leads to fluctuation relations. Okay. So you may wonder why now. So there's 100 years of the quantum mechanics. This year is 100 years of the UNESCO declares the year of quantum physics, because it's 100 years since the Heisenberg paper. Why are this framework being introduced only recently? And the reason is that if you look only at the level of averages of variances, then there is no differences between the two approaches. Only when we look at finer properties of this to measure, then the two approaches are not equivalent. And so let me emphasize again that in this definition of the fact that we measure the system comes heavily in the definition, because after first measurement, the act of measuring the system will perturb the state. And so your initial state will reduce. If you observe an outcome J, then will collapse. Okay, and so then you have modified the system by measuring it first. And so this is a fact, and so the introduction of this framework comes with a price of the fact that you perturb the system by measuring it, and it comes with some then surprising phenomena which you may or may not see as a problem. So that's open to discussion. Very good. So what it's now we can you have a functional which is defined in the confined finite approximation. So is it possible you want to take the limit for n going to infinity? You want to describe infinitely extended reservoir. So is it possible to rewrite this object in terms of in a way that we say will survive the thermodynamic limit? Meaning, so you have to write it in terms of some algebraic expression will still make sense when you take n going to infinity. And is it possible to do so? And that corresponds to the same formal expression. So in other words, if I follow this physical line of thinking and define this f of omega t obtained through thinking of a two-time measurement framework, and then take the limit for the n going to infinity, or if we think in the spirit of quantum phase space contraction, so in the spirit of generalizing the radon-Nikodym derivative, then it turns out we obtain exactly the same thing. This is the same formula that we had before. So,
Annalisa, when you
yes.
say the same formula, you're saying that the same formula as Tasaki Matsui case?
Yes.
Oh, okay.
Yes.
Oh, that's
Yes.
interesting.
Yes.
Thank you.
Yes, exactly. So this, I mean, we joke amongst co-authors is a little bit of a miracle. So why this always came a little bit could be considered surprising, and the connection between these two approaches have been explored and pointed out in the lecture notes of the election of Jaksic, Ogata, Potrapille in 2012. So this is a lecture note where they wrote down and explored all the connection between these two approaches. So very good. So now this is what has been done for the transient case. Now our result concerned the steady case, so we want to consider now the other setting. This has not been done yet because there are several problems. So the first problem would be that from a conceptual physical way that the measurement would destroy the steady state. And another one is that steady state exists only in the thermodynamic limit, and in the thermodynamic limit, the state you will obtain will be non-normal with respect to the initial state. So so some of you know what non-normal means. For those who don't, let's say the states are very, very different. So in particular, you cannot write the equivalent of directly the equivalent of a radon-Nikodym derivative. So a short way to say it is many things that you would like to write does not make sense. You have to find a way around it. Okay. So our starting point is to extend this fluctuation or right fluctuation function for a state which is not the initial state omega. Okay, so we want to extend the theory. So let's start with a state which is not too far from omega, in the sense of which is normal from omega. You can think of a state which is, for example, a perturbation of omega. Okay, so is it possible to write? We take the two-time measurement approach, so we can write everything in the finite setting. This time, my initial state will be the state nu, which is not omega. And is it possible to write this as in algebraic, so manipulate the formula in order to have some algebraic object that will still make sense in the thermodynamic limit? And the answer is yes. So with us is new formula, which is this one. This is a result of there is a result in the first paper that was listed of 2024. Okay, so to compare with so I wrote this more compact version through the cocycle. So to compare, this was the formula we had from omega, and you see what we had to do here is to take the ergodic averages, okay, with respect. So this is essentially we are taking an average with respect of a dynamic, which is called modular dynamic associated to omega. Since here omega is a equilibrium state for the free dynamics. This you can see as the free dynamics, so the dynamics before you couple the two reservoirs up to a temperature time, up to a scale factor, which is proportional to the temperature. Okay, so this is basically the difference with what was before is now you have to take averages with respect to the free dynamics before you couple the reservoirs. Okay, so now this allows us to write the entropic functional for a state which is normal to omega. One could invoke a density theorem and say now by Fell theorem, and this will be defined for the non-equilibrium steady state. But in order to have an understanding of the physical picture, now we want to really find a way to approximate the steady state. Okay, so the core idea is to go back to how we see the steady state. As the steady state, we want to think it as an idealization of the initial state, what has evolved for a very, very large unknown time. So then we'll take the limit to this large time going to infinity. Okay, and now what one can do is to think that now I am still applying the two-time measurement protocol, but this time I performed the first measurement not at time 0, which corresponds to taking the initial state, but at a very, very large time, capital T, which corresponds to taking as initial state the state omega evoluted at time capital T. Okay, then we can do the same. So the same procedure. So you perform the first measurement at a very large time, capital T, let the system evolve for a finite time, small t, and then perform the second measurement at time capital T plus small t. Okay, so this leads to a well-defined probability distribution in a confined case. And then we've seen by the theorem before, you can also extend, so it will also, you can also write this for infinitely extended reservoirs. And then we will obtain then therefore this functional, and then our proposal for the definition is to take as a quantum static entropic functional the limit for t going to infinity of this one. Okay, so I'm performing the first measurement at a very large time, capital T. I write my functional, and then I let large time, capital T, go to infinity. And that is what we call a quantum steady entropic functional. Okay. Very good. So if that is okay, then what happens when I consider this object? And as I said before, then there are some surprising effects that have no classical counterpart. So the first theorem, I think it's clearer if I first explain the case when the two reservoirs are coupled directly. So here there is no small system. I just coupled the two reservoirs directly some way. Under a very, very light hypothesis, we just assume that the reservoirs are ergodic with respect to the free dynamics. So this is a very light assumption. Then the two functional are always the same. So the time where we perform the first measurement doesn't matter. The act of measurement, coupled with the fact that you consider the thermodynamic limit, we just erase completely the memory. And so these two functionals will be the same. Okay, so then of course, when you consider the limit for capital T going to infinity, then you have this is equal. This is equal at finite time. That was not true in the classical case, typically not true. So the system, the symmetry is also true at finite time, and okay, the limiting generating function are of course equal. now, if there is a small system, then you don't have a quality of finite time because in what we are doing, we are measuring only in the reservoir. So we measure the entropy in the reservoir. So the small system stay untouched. So you don't have a quality of finite time, and only because the small system is not touched. But of course, the small system is small with respect to the reservoir, so its role when you take the time going to infinity, when you want to look at the fluctuation for a time going to infinity, will be neglectable with respect to the reservoir. And then, so when you take the limiting object, when you take the time going to infinity, the small t going to infinity, then the quality is restored. Okay, these are the the first result, and also I already try to give you the elements of why this is true. So the underlying mechanism, again, is the fact that there is a very invasive role of measurement. This really comes in the definition of the total measurement framework. And because on the, we are taking the thermodynamic limit, and the reservoir is ergodic, so you basically have to, when you measure, you project on the invariant state of a system, and because because the reservoir ergodic, that is only the initial state. So you are really setting back everything at time zero. Our proof is general with algebraic methods. So there are no additional technical hypotheses. We are in the frame of a sister algebra, so it is mainly applied to fermionic systems. And again, there are no hypotheses on the perturbed dynamics. This depends only on the fact that the reservoir are ergodic with respect to the free dynamics of before a couple. Okay, and then this way we were able to cope with the non-equilibrium steady state in the thermodynamic limit. Very good. So let me sum up so far. So we have introduced, I have tried to review the classical entropic function, and we have reviewed the quantization of the transient case, which led us to understand why it's necessary to introduce the total measurement framework. And we have introduced a proposal from the quantostatic entropic functional, which corresponds to the formulation of the Galotti-Cohen. And the result we have is that in this case, there is a very strong memory erasing effect, which is due to the very invasive role of a measurement in the thermodynamic limit. You can also interpret this as a sort of stability with respect to the time when you take the first measurement. This effect is purely quantum. There's absolutely no classical quantum part of this, because it depends on the act of measuring, which has always been one of the difficulties of the problems of quantum mechanics. So we will have equality of the two functional under minimal ergodicities hypothesis, so which is very different again than the classical case. Now, you may ask, so that you may have some criticism. Maybe you are thinking of things that I didn't think about, but you probably are you're thinking now that yes, there is a catch in what I've been saying to you, is that we are taking direct measurement on infinitely extended reservoir. So this is a high idealization, which is not really implementable in a lab. So you may think about it. So the natural question that you may be asking yourself is, are we able to write similar, maybe less general result in the framework of indirect measurement, right? So, and the answer is yes. And this is the next subject that I want to cover. Okay. So now we consider now what is called ancilla state tomography. Ancilla is Latin for servant, so basically you are just using an auxiliary system that is called ancilla. So we are coupling our entire systems, the small system plus the reservoir, to another system, an auxiliary system called an ancilla. I'm doing this description in starting with a confined approximation in the finite dimensional case. Okay, so now we are, so you couple your system with an auxiliary system. You take a spin. You can take just a two-level system. And then what one can do is to introduce for each alpha a family of an Hamiltonian which manufacture an interaction. You can manufacture an interaction between your auxiliary system and the rest of the system in order to have that when you take the evolution at the time t of what's happening in the auxiliary system, then one can prove that it will give you a state which the off-diagonal part are proportional to the functional that we got, okay, that we want. So, okay, so let me say it again. So you couple the system, you let it evolve for a time t with this auxiliary interaction H alpha. Then you look at what happened in the auxiliary system, and then you see that, so you can prove that this must be the state at time t, and then you can measure the state of a system through a state tomography, meaning that you have to reconstruct the state by measuring several copies of the system, of the ancilla. Okay, so so this way you have access to f omega of t, but you're never using a direct measurement of infinitely standard reservoir. You're measuring a two-level system. So this can be also written in a general way, okay, in a more abstract way. And so I want to emphasize here that here I have made the story short. I say, okay, this is just equal to this, but in order to prove this equality, you have to go through several passages. And in the end, if we start with the initial state, okay, sorry, we have to do several passages. So we defining an auxiliary, the ancilla functional, something that comes, it's one of the steps, let's say steps before you do the final steps in order to have f omega, okay? And these final steps works only if you take as state the initial state omega. But as soon as we move from that, so take another state, or we perform the first measurement a bit later, then you will have that these two functions are different, okay? And so what's happening now? So what to do now? So the protocol of the ancilla coupling is not invariant with respect of the time capital T, or if you prefer, with respect to the initial state you take. In the way I present you the subject, you have no reason to think why it should be stable. Right? It would be, you know, okay, I will manufacture something that works for omega, what should we work for another state? But in the physics literature, they seems to think that this procedure has a deeper meaning than one should expect some stability. In both cases, whatever is your interpretation of this ancilla coupling, it is natural to ask yourself, is this protocol stable? So meaning, okay, these two are not the same, but is the equality, are they maybe almost the same? Is the equality of the limiting functional restore in the limit for t going to infinity, right? So this E omega t and omega that I showed before are the same. And the answer is yes, but not in general. So if I take omega t with capital T finite, then it's true, but under some additional hypothesis. But we can have a general proof. Otherwise, if we really want to consider the limit for capital T going to infinity, so the non-equilibrium steady state, then this is expected to hold true only under additional chaoticity hypothesis for chaoticity property of the dynamics. And so it has to verify the model by model. And we propose a general scheme to do it, and we also were able to prove it for the spin-Taylor model. So one can argue that when look at ancilla state tomography, then there is a parallel with the classical case, which is restored, because now you don't have a quality just like that. You need to add the chaoticity hypothesis, and you need to verify model by model just like in the classical case. And so let me end this presentation by telling a few words more about these other results. So for the result for T finite, okay, holds, so we are able to write an equality of this type that, of course, entails the equality of the limiting objects. So this is hold true under an additional hypothesis, which can be written in abstract term like a property of an analytic extension of this map. So this was the interaction, and this was the free dynamics. Okay, so basically you can identify this essentially with the free dynamics. In concrete models, this turned out to be a ultraviolet control of the coupling function. This is a hypothesis on the ultraviolet behavior of the coupling function. So your coupling function must decay fast enough at infinity in order not to allow too many jumps between energy jumps between a measurement and another. You have to control, let's say, what happened in the ultraviolet region. So this is somehow a very natural hypothesis too. And for the non-equilibrium steady state, as I say, we are able to draw a sort of a general scheme in order to prove this kind of property, but it has to be verified case by case, and we were able to verify. We wrote the last paper of a series deal with the spin fermion model, which some additional regularity hypothesis which allow you to implement the techniques that are used in order to have this result. But they're probably more like a technical hypothesis. So, okay, so just a last comment. So again, we have introduced several kind of functionals, okay, which once following the phase space construction, once following the two-time measurement framework, the physical idea of two-time measurements, and we also have introduced the functional concerning which the functional related to indirect measurements. And let me emphasize again. So if you take as reference state the initial state, okay, the thermal state, then all these functional are the same. You don't have any problem. But as soon as you move from that, then quality anymore. However, under additional hypothesis, some of this equality can be restored in the limit. So I've shown you before. The theorem I showed you before is for the ergodic reservoir and some kind of ultraviolet hypothesis for the limiting objects. Otherwise, one has to go model by model. Very good. So this was my last remark, and I want to thank you for your attention.
So thank you very much. Questions, comments? You can directly unmute yourself.
Can I start?
Yes.
Yeah, thank you very much. Yes, it was difficult, but I think I learned a lot. So, first of all, so you compare the case with indirect measurement with naive to time case. And you said that in some case, like bath or pure thermal, then they are identical. Is that correct?
Can you repeat, please?
Oh, so you compared this functional for the case with indirect measurement
Yes.
and for naive to time measurement scheme.
So wait, there is naive scheme is the one who doesn't
Okay, no,
use
just
fluctuation.
not naive, but two-time
The two-time measurement,
two-time
yes.
measurement, yes.
And then,
And
yes.
for me, they seem to be very different. I mean, they seem to represent different physical processes. So why should this functional be the same even in this multithermal state? You are doing different measurement, different experiments, right?
Yes, so because you have manufactured, so this is a question concerning already the fact when I take the initial state. So here you have chosen your interaction in order to have this. That's what people do. I mean, physics community seems okay with that. I am, you may be critical. This is something that you choose in order to have that your ancilla state will be like this. So you have to introduce this. So basically, you are manufacturing a coupling so that
it's a
you
really
can
tailored.
obtain this. That is what people do.
Okay.
So now you may say, okay, but I have to measure for every alpha and I have to take a state tomography. So maybe this is also a sort of idealized case.
Okay.
Okay. So it's true because I have chosen interaction in order to have access to the object I'm interested in.
Okay, thank you.
So maybe just following this, because I probably missed this. So here it's important that you're using in this auxiliary system spin 1/2. I think I missed this.
Well, I am taking an auxiliary system. Okay, so I'm taking a spin, which is it has to. So it's a simpler case now because I have only two entries. Right. So I'm not thin, so I guess you could do it with a bigger system, but that would have added complication. So we did it in a quicker only for a spin.
I see. Other questions?
Well, maybe let me ask, but it's, let's say, a very imprecise question. So recently in high energy physics, algebraic quantum field theory, many people are also computing relative entropies because of their connections with energy conditions, which you use to exclude exotic spacetimes, this sort of things. I don't understand their motivation completely, but it's something in this direction. So I was wondering when listening to your talk if there is any connection in intention maybe or in motivation with these developments which you discussed.
So I'm not sure I'm aware of what you're talking about. I know that so people may be interested. So you talk about curve space-time. So.
Well, I'm thinking about what Roberto Longo and his group have been doing. So a lot of computing of relative modular operators for various pairs of states. So technically, there are definitely similarities to
Yeah, so
we are
certainly, so
doing,
in that community, they also use the modular theory, let's say, in order to describe entropies. And I think their problems they look are very different. And I want to learn more what they're doing, but I'm not able to answer you in a...
Okay, well, maybe you can comment a bit on your motivation. What is, maybe it was in the talk, I just didn't get it. So what is, let's say, your favorite physical situation to apply this theory?
So the physical motivation is the one to study entropy fluctuations in statistical quantum mechanics. So the main application is you have two reservoirs and you connect them, and you want to establish what are the properties of the quantities that will be, transferred from one reservoir and another. So the entire
I see. So it's a
plain
small system interacting
on
with.
equilibrium statistical mechanics, and you can also, for example, from this functional, you can also deduce, use it to obtain a linear response theory, or yeah.
Maybe it was in the talk hidden. I was just not attentive enough. Do you also look at relaxation to equilibrium?
So you can look at that, but here we are looking at the situation where you try to. Okay, in this particular talk, we were thinking of when you don't reach equilibrium, but you can you reach a non-equilibrium steady state. So you have a regime, you have a flow from a reservoir to another. But you can definitely use a similar technique in all the problems of relaxation to equilibrium.
Yeah, so this is again popular in quantum field theory in the context of Unruh effect. So there were recent works, maybe by Fesch.
I mean, they don't really. So at least as far as I know, they. So there are certain things that I don't know very well, that certain entropies that are studied because you localize yourself in a certain subject, in certain subspace, right? So you want to see, okay, what is the entropy if I restrict myself on a certain space of so for example, in the Unruh effect, I guess they look when you restrict yourself on the wedge, or there may be problem of that type. That kind of problem, I have a feeling just like you, but I don't want to say anything.
Yeah, but there is a technical similarity, because I think the end we also look at kind of spin boson system, so a two-level system coupled to quantum fields, which is, I guess, not so far from what you are doing.
Talking of that to call the Bièvre.
Yeah, they use methods from the Bièvre.
Yes, so in the Bièvre talk, this is a similar setting, in the sense you couple a small system which you interpret as a thermometer to a field, except the fields live now in space lives so that you are you are describing an accelerated particle, and you want to see what the thermometer use in just looking how there will be a relaxation, no, of the thermometer to the temperature of the field you couple it with. So that is in a similar framework, but that's how it has more or less a similar framework, similar technique, but there are no entropic functions.
Yeah, so we are not really looking at entropies.
But it is, you also use modular operator, and then you also, what they do is to use the Liouvillean approach, which I've not talked about, but is what we used in, so at some point you want to translate this, the object you look at with the expectation value of exponential of an auxiliary operator called Liouvillean, which is similar to the one you're used in quantity theory. So that's what
Okay,
I'm
thank you.
thinking about.
More questions?
Yes, can I ask one more question? So it is very interesting that this mathematical object that Tasaki Matsui introduced plays some role, or probably essential role in this approach of two-time measurement and so on. So could you give a simple intuitive explanation why are they these?
No, I mean, I wish in the sense that no one there's no so if you I can give you the explanation, you write it down and then you end up to be the same, but I cannot give you an a priori explanation in the sense it's not just me. This is not my fault. It's just not completely understood, or at least I don't have so the best explanation is somehow that you had Tasaki Matsui, they use the relative modular operator, which is the quantum Radon-Nikodym derivative. So you must arrive to something that makes sense. But why this encodes but this encodes really the measurement. It's something that you can easily prove once you have the formulas. So just write it down. It is the same. But I think the community does not have an answer to this question. We often joke and we say this is a miracle. It's a miracle theorem. It's exactly the same.
Oh, that's interesting. Thank you very much.
Oh, I don't see any other questions. So, ora? No? Okay, then we can thank the speaker again. And we can stop the recording.